Hi, everyone. It's Will. Welcome to the miniKanren intro hangout number 3. And we're going to start with some questions from last time. The other thing I'd like to point people to is a new resource. So Nahal from the other hangout series has suggested that we sort of collect our code and links to videos and things like that in one place. And so we started a GitHub repo, and I'll show you what the link to that is. There's my Emacs, there we go. Okay, so let me turn off my air conditioner. Okay, here is the link on GitHub to a page that contains various pointers to the intro and advanced videos, and also short descriptions of those videos. And we're trying to get it organized to the point where we'll actually have the different topics time coded, so you can just click on a link or go to that time in the video. So if you want to learn about continuations or whatever it is, you can just go to this page, see what the topics are, or search for continuations, and then you'll find which videos talk about that, or some other topic that may be related to Scheme or miniKanren or whatever. So we're trying to get a little more organized. For the advanced Hangouts, we also have something where if you want to talk about a topic, you can sort of sign up to talk about it in the future. And also, we're putting the code in the Hangout, so from the Hangouts up there. So the code from last week's intro Hangout is on the summaries page. So and the code here will also be on the summaries page. Okay, so let's start with a few questions from last time. So Louise had some really good questions, and first question she asked is about Quasiquote, or backquote and comma and regular quote and all those sorts of things. And this is a topic that in some sense it's not super complicated, although if you want to actually implement Quasiquote in a nice way and unquote in a nice way and unquote splicing and all these operators, it is non-trivial to do a nice implementation, I think. But reading these expressions and trying to figure out what they evaluate to can get kind of messy once there's a certain amount of nesting, and trying to figure out when an expression is going to get evaluated if it has a comma in front of it, that sort of thing. So the example Louise gave is this example, this backquoted expression or quasi-quoted expression. And if you notice, there's a comma or unquote before this call to car, or what looks like a call to car. And if you look at the value that you get back when you evaluate the quasi-quoted expression, we still have the call to car. And I think this was initially confusing. And what you realize was that it's because we have a quote in front of this list that contains the backquote. And you correctly realize that if you have a quote, then once you're in the quoted environment, this backquote, or sorry, the unquote doesn't behave like it would if you're just within a quasi-quote expression. So if I did a, the car, quote EF, and so I just grab sort of the last part of this expression up here. If I put that list within a quasi-quote environment, or quasi-quote the list, then you'll see that I'm actually taking the car. So the comma in front of the car expression means that I'm going to evaluate that expression just like I would at the REPL, and car of quote EF by itself is going to give me E. So therefore, this comma or unquote car quote EF is going to evaluate the E, and sure enough, that's the answer we get. However, as soon as I put that comma in front of the list beginning with D, now this entire list is quoted. Okay, so I'm just going to treat that as data. And so therefore, what this comma really is, so if you remember what comma is actually unquote. We get rid of all of the shorthand. Let's get rid of all these shorthand things to see what's going on. So this is a quote. This is a quote. And then here we have a quasi-quote. Okay. Sure enough, that evaluates the yeah. So once I put the quote and a quasi-quote, or once I put this quote around this entire list, basically I'm just going to get back whatever I put in there, which is a quote of this D thing. By running that by itself is the list D with a comma in front of car quote EF. Was a quote a quote. Wait, okay. Hold on a second. I'm getting confused now. Did I do something wrong when I converted it? Quasi-quote list. Oh, no, I did that right. Okay, quasi-quote A, quote, list D, unquote, car, quote, EF. All right, hold on a second. All right. Well, that was a good question, Louise. Let's go back to the original. Okay, so let's count our back quotes under commas. So we have there. All right, so we have this quoted. This is unquoted expression. Oh, no, that's fine. Yeah, okay, so I'm doing something wrong with my other thing that's supposedly a simplified version of the expression. So what did I do wrong? All right, so let's be a little more methodical about this. Okay, so here's the first expression, the original expression. Now I should be able to get rid of the second expression. Oh, I was misreading this. This isn't working at all what I thought it was, actually, Louise. This is a good question. Okay, so this expression, I miscounted my parens. Okay. I thought this was a different expression. I'll tell you what expression I thought it was. I thought it was an expression where the append was coming after the comma by itself. Yeah, I don't know how I got that wrong. I thought it was something more like this, and this was the end of the append. And then we had a separate expression here. I'll show you what I thought it was. I totally misparsed that. I thought we had a quasi-quoted list that had 3 sub-expressions. The A, which is just going to be a symbol because it's quasi-quoted, and then a call to append, and then another quoted expression. Okay, that's what I thought it was. I didn't realize the entire append was unquoted. Okay, wow. See, and look, I explained it wrong too because I got that answer wrong. So let's take a look first at the expression that I thought it was. So here we're first of all, if I put a quote in front of the entire list of 3 elements, then we're just going to get back exactly what I put in. Okay, we're just getting back those 3 elements exactly like I put it. Let's just make sure that's correct. Yep, that's correct. Okay, so that was the input, and this is the output, and you can see that we're just getting back the same thing. Okay, that's just what quote does by itself. It's just, we're just going to get the data back. Now within the Quasiquote environment, what do we have going on here? So the first thing we have is this, this A, which is going to be a symbol. Then we have this call to append. Okay, so this call to append, this is unquoted, so the entire call to append is unquoted. We'll evaluate this just as if we were in Scheme. And here, we don't have any unquotes within this. Or actually, we're already in an unquoted environment. So the Quasiquote and the unquote cancel out. So this should be the same as if I had just typed in the append itself at the top level. So I should get cooter, quote, ABC. All right. And cooter, quote, ABC, that is indeed what I get back. Okay, so that part we're okay on. And then down here, we're still in the quasi-quoted environment for the third element, but now we have this quote thing, great. And then we're creating this list. So, this quoted list of D, so we should have quote, and then the list containing the symbol D. And now here's the interesting thing. So what I said was a lie before, that if we're in a quoted environment, that the comma doesn't have an effect. We're still in this quasi-quoted environment. The comma still actually does have an effect. So at this point, the quasi-quote and the unquote cancel out. So this is just going to be like if I did car of quote EF, which is just E. So I expect to get back the quoted list DE is the third element. Yep, is quote DE. Notice it has a quote in front of it. So just because we're in the quote doesn't mean that we cancel out, that we ignore this unquote. So this still takes effect. Okay, so let's go back to the expression that you actually wrote, which I totally misparsed. But actually, I thought I was going to do something different. So I thought this comma was going to sort of get turned into just data because of the quote, but no, because we're in the unquote environment, this comma still has a meaning. Now, once this comma cancels out the unquote, now this car expression is just as if we had typed it at the REPL, at the top level, and that's just going to value to E. And this quote here, because it's inside the unquote, because we're inside an unquoted list, this quote still remains on the output. So that's why we see the quote symbol. But we're still going to evaluate that call to car. All right, so I screwed that one up. I thought we were going to get something different. So I need to look at the unquote definition to understand exactly why that's not working the way I thought it did. All right, but the expression you gave me wasn't what I thought it was. It wasn't a quasi-quoted list of 3 sub-expressions. There are only 2 sub-expressions. So A is just going to be a symbol. And now here, this actually is easy to understand compared to the other one, at least for me, because we have a quasi-quote and we have an unquote. And these cancel out. So this should, the value of this expression should be exactly as if I just grabbed that whole append call and just typed it by itself. So we should get cooter, quote, ABC, D, this unquote, and then everything else. And sure enough, you can see that's what we get. That second sub-expression in that quasi-quoted list evaluates to what we had gotten if we just typed append at the top level. So if the lesson there is that the quasi-quote and the unquote cancel out. So if I say quasi-quote, R of ABC, so this is a quasi-quote expression with no unquote, so therefore I'm just treating everything as data. But I can immediately put a comma, an unquote, inside the quasi-quote, and this basically cancels out both the quasi-quote and the unquote. That's the same as if I typed it by itself. So the unquote basically annihilates or gets rid of the quasi-quote. And so if you have a quasi-quote and then an unquote somewhere immediately within inside that quasi-quoted environment, the expression you have inside of it is just like you didn't have a quasi-quote at all on the outside. Okay, but I did screw up my understanding of the other one, where this is the one where I had this expression where you have a quasi-quote, and then you have a quote, and then inside of that quoted list, you have the unquote. So the quasi-quote and the unquote cancel out. And so at this point, yeah, it's the same as if we had typed that we were in this quoted environment. And I was thinking, oh, okay, so we're in a quoted environment, so therefore we're just going to get back the that entire expression with the unquote preserved, but not. But nope, because we're in a quasi-quote environment, the unquote still means evaluate this. So that confused me. I need to go back and look carefully at the specification. And one of the things I'll say is, if so this is actually a great example to look at. I mean, I've been doing Scheme for a long time, but these sorts of expressions aren't ones that I do on a normal basis, because normally I'd write this expression in a different way, because you can write these things in parts, usually pieces parts. But I'm still learning Scheme. There are lots of parts of Scheme that I get tripped up on occasionally. So what do I do if I get tripped up on something like this? Well, the thing to do is look at one of two sources usually. Usually, if I don't understand how something in Scheme or any other programming language works, I will look at some sort of book, which is, if not a tutorial, at least it's some description of the language in English and with lots of examples that talks about how the language should behave. And then I'll also look at the specification for the language, if there is one, if there's a formal spec for the language. I'll look at that, and then I'll just try a bunch of examples as well to try to test my understanding. So in this case, I will try to show you very quickly. So what would I do? So I'd bring up a web browser, and one resource I use is the Scheme programming language, 4th edition by Kent Divig. And this is available, you can get it bound, but it's also available online. So scheme.com TSPL/4 or /4, okay. The Scheme programming language, 4th edition. And this book's awesome. If you go to the index, we can look up Quasiquote, for example. And now it's got a whole section talking about Quasiquote, unquote splicing, and it has lots and lots of examples. And so you can look there and try to figure out exactly what the meaning is. So Quasiquote is similar to quote, but it allows part of the quote, part of the quoted text to be unquoted. Within a quasiquote expression, unquote and unquote splicing subforms are evaluated, and everything else is quoted that is left unevaluated. Okay, so that's what's going on. So that quote itself is being unevaluated. We're not actually treating that quote as something special. So that's why I get confused. The value of each unquote subform is inserted into the output. Okay, and so forth. And it shows a bunch of examples here of these things. And then the other place to look at is we can look at R6RS Scheme and Quasiquote. So let's see if I can find Quasiquotation. Okay, so this is the current complete version of the specification. There's a later version called R7RS. All the Scheme specifications are R something. So R5RS was the Scheme spec that was in place when I got started. R6RS is sort of the most recent complete spec for the full language. And then R7RS is a specification that's still going on. And for that specification, they've decided to break the language into a small part and a big part. And they finished the small part specification, and they're still working on the big part specification. So I tend to look at R6RS because that's what most of the implementations today support. And so you can see there's a section here on quasi-quotation and it has lots of examples and describes the behavior. So if you look at the Scheme programming language 4th edition and look at those examples in that description, and if you also look at the specification and then do some examples on your own, then you should get a pretty good sense of how it works. And so now, from reading in Kent's description, I think I have a good idea what's going on. So my mistake, the mental error I made, my mental model was wrong. From doing the simple interpreters that we normally write, or I normally write, I normally think that quote of some datum evaluates to that datum. That was the model I was thinking. And when we write an interpreter, like a simple version of quote, that's exactly what will happen. But we don't have a quote form on the outside. We have a quasi-quote form on the outside, and the quasi-quote rules are different than for quote. And so the way the quasi-quote worked is if you have a quasi-quote expression, then everything in that datum is considered quoted except for expressions that are followed by unquote. And those are considered, you evaluate those normally. So the thing where I got confused was this quote is inside the quasi-quote form, but outside of a comma. So therefore, we're not evaluating that quote form. We're not using the normal rules for quote. We're not saying that quote of this datum is that datum. This quote doesn't mean anything. That's just a symbol. So if we do go back and expand it again, let's see, quasi-quote. So this is a good question, Louise. This helped me figure out something I didn't know. And I didn't know it, which was even more helpful. Here's unquote. And quasi-quote. Sort of what it looks like it's been. And here's the quote. Shouldn't say. Well, there's once the sort of special shorthand text has been expanded. This is a quote. Unquote. And this is a quote. All right, and we should get back the same answer, and we do. All right, so let's look what's going on. Here's quasi-quote. So now we're inside of a quasi-quote, and we have one list inside of the quasi-quote. And that list contains 3 sub-expressions. A, this list, and this list. So A is going to be quasi-quoted. So basically what we're doing is we're treating everything here as being quoted unless there's a quasi-quote form wrapped around it and on the outside. So A doesn't have a quasi-quote form. I mean, sorry, an unquote form. Did I screw that up? No, I got my unquote right. Okay, good. Unless there's an unquote wrapped around it, then we're just going to treat this as if it's quoted. So A is going to be, we're just going to treat that as being quoted. So that's just going to give us the symbol A. That's fine. This entire list is wrapped with an unquote. So the rule is we evaluate this as if we just made this call to append at the top level. So, I can pull that out, run that. And so that expression should be cdr of quote ABC. So we know we're going to have the symbol A as the first element in the list, and then cdr quote ABC is the second element in the list. And sure enough, that's what we see. We have A, and we have cdr quote ABC as the second element in the list. Okay, and now let's look at the third sub-element in the list. And the tricky part, well, it's not tricky. I just got confused. This is not an unquote form. This is a quote form. So therefore, we treat the quote form as if that was quoted as well. So in other words, we're not going to evaluate the quote according to the rule of quote, that quote of datum is datum. We're just going to forget that we know that there's a quote form that even exists. This could have been called foo. It doesn't matter to us. It's not going to have any effect. So this quote doesn't matter that there's something in Scheme called quote. We're just going to output it as QOTE. And this list, D, this is all quoted. So we know we're going to get back a sublist that contains a D. And now we get to this unquote. So that unquote cancels out the quasi-quote we're inside of. And then this car itself, that expression we evaluate and get back E. Okay, so we're going to end up with a quote of a list, D, and then the value of the unquote expression, which is E. And sure enough, we get a quote in the list, DE. So that's right. Okay, so the key insight here is that once we're in a quasi-quote, once we're inside a quasi-quote, unless we see an unquote at the top, working inside out, that's going to cancel that quasi-quote, then we just ignore any scheme forms we see. Those are just considered quoted symbols. Okay, so we're going to see quote coming out, and it just happens to be that the shorthand for QOTE is that quote symbol. So that's why we're seeing the quote symbol DE. All right, that was insightful. That actually helped me a lot. So thank you, Luis. That was that was a very good question. All right, so where's yeah, here's my Hangouts. Stop that screen sharing for a second. Okay. Does that very roundabout expression explanation help you out, Luis, or did that just confuse you?
No, that helped me out. That was great, and okay. It was helpful that you showed the other example, because that made it even more. That showed even more what's going on. So now I'm fine.
Yeah.
Thanks a million.
Sure. So your example actually wasn't confusing to me, but the other example that I interpreted was confusing to me. So that was good, because the other thing is it got to show you, like, okay, well, what should you do if you get confused about how scheme behaves, right? Look it up in the Shea scheme programming language, look at those examples, look at the description, look it up in the spec, try some examples. And so now I have a much better understanding of what's going on. So that's outstanding. Thank you. And so, in fact, just to make sure I really do understand what's going on here, I'm going to create a quasi-quote expression just to make sure I understand what's going on. So I'll say A, B. Now I'm going to sort of stress test my understanding. I'm just going to have a whole bunch of quotes here. And now, inside of all this junk, I could say C, F, or something like that. I'll put in an add one of 3 or something like that. Yep, and add one of 3 evaluated to 4. So the fact that I have a zillion quotes here doesn't matter, because those quotes aren't acting like schemes quote. It's not quote of datum, it's datum. Because we're in this quasi-quoted environment, those are just symbols. That's exactly like if I'm just getting the symbol back, just like I'm getting back the symbol A and B. Those are just treated as quoted symbols, those quotes. That's great. All right. Now, one thing I will say is that unless you're doing something tricky with quasi-quote, unless you're trying to build up some really complicated expressions, what you could, normally you don't even need quasi-quote. Quasi-quote is something where you can build up the list just making calls to lists, for example. List quote A, quote B. I could start building up lists like that, and I can use cons and so forth. The other thing I can do is I can use let to let bind sub-expressions, and so I could build up a very complicated sub-expression, and build up all these sub-expressions and then put them together with a call to list or calls to cons or whatever, and give names to the sub-expressions and things like that. So I could say, E1 is list quote A quote B, and E2 is, I don't know, list. And here I can put in expressions I want to evaluate. I could say this is list C, add one of 3, and list quote C, add 1 to 3, quote D, stuff like that. And then I could do things like, build up a list containing E1 and E2. So that's another way to create these lists. And notice I evaluated the add 1 of 3 to get a 4 here. So, if you ever get to the point where you're really confused about the quasi-quote and the end quotes, you can also just break the expression down and let bind the parts and give them names and things like that. Unless you're doing something really tricky with generated code, you can just do these sorts of tricks normally. So anyway, if you do have some hairy back-quoted expression, you can often break it down to something simpler. But that was the key insight: is when you're inside the back quote, you just basically treat everything as quoted until you see an unquote. Good question. All right. Another question was, last time we were talking about how let works, and so we were just seeing some. So let's see. So let x be 7, and the body is times xx, and we said that maybe it's the 49, and we also say lambda x with a body of times xx applied to 7 evaluates the 49, and 49 evaluates the 49. And I said that this let expression is equivalent to this left lambda, this direct application of lambda. Those are equivalent expressions somehow. And that, remember, if we wrote a little macro, we defined basically mylet using syntax rules. So syntax rules, and so we've got body, x, sorry, whoops. So x has value of some expression, and then we have the body, and we say that mylet evaluates to the same thing as if we had written lambda x body applied to E. So that was that this works. So mylet of x being 7 with the body of times xx. So, oh, this is defined syntax. Yeah, if you don't do that, you will get the wrong thing. Yeah, it gives me 49. Okay, so when I was talking before about the direct application of the lambda, this left lambda thing we call it sometimes, lambda expression being applied to an argument immediately, being equivalent to the let expression. What does that mean to be equivalent? So here's the lambda expression being applied to 7, and here's the original let expression. And I said that somehow those expressions are equivalent. What does it mean? In computer science, we're often talking about something being equivalent to something else. In this case, I meant that they evaluated to the same value. Okay, it's guaranteed that we're always going to get the same value back and the same behavior from those expressions, actually. And not just the value we get back. There are other types of behaviors we can get that I haven't shown you. For example, like printing out an output or reading from a file or something like that. So there are other types of behaviors that the let expression could have, or the direct application of the lambda expression could have. And in all ways, it's indistinguishable. So what I mean is, if I give you some other, well, I have to be a little careful how I say this because Scheme has macros and you can play all sorts of tricks with those. But generally speaking, you're not going to be able to tell any difference between using this left lambda expression, the direct application of lambda, or using a let. You should be able to replace any let expression with the left lambda and vice versa, unless you're doing something, very, very strange with macros or writing your own interpreter and you decide to handle let differently than lambda. But just in scheme, you could go back and forth between these two forms, and that's part of normal scheme semantics. And we saw that when we tried doing expand and Shay. So we took left lambda expression, oops, and we tried seeing what it expands to in Shay, and we saw that it turns into a let expression. And we saw it has these gensimi things also. But the bottom line is it turns into a let expression. And if you expand the let expression, we saw that just stayed a let expression. So that thing still is a let expression. So you can see that internally, Shay is turning this left lambda and turning it into a let. So those are equivalent expressions in that you would expect them to always evaluate to the same value, to always have the same behavior. In other words, it doesn't matter which of those expressions you use. Now, I hedged my bets a little bit because Scheme has a very, very powerful macro system. If you're using Rack, it has a macro system has even more bells and whistles. You could be writing an interpreter for a subset of Scheme and change the evaluation semantics a little bit, in which case you might change the meaning of let, make that behave a little differently than left lambda. But in just sort of vanilla Scheme, if you're not doing any sort of very strange macro, like there's a macro extension in Racket, which is called local define. If you're not doing a tree walking macro system like you would have in some versions of Lisp, where you can actually look at all of the syntax and treat that specially. If you're not redefining the behavior of let or redefining the behavior of lambda, which you can do, you can write macros that, you could redefine the behavior of let to do something different if you wanted to. But if you're just in normal Scheme, you're not doing anything really, really outside the normal bounds, that left lambda and let are going to be exactly equivalent. You're not going to be able to tell any difference, except that syntactically the program might look a little bit differently, but they'll always evaluate to the same expression. Now, this whole concept of what does it mean for two things to be equivalent actually can get very, very tricky. And especially when you talk about in which context, in which programs is this expression the same as this other expression. And it turns out that there are all sorts of things in Scheme where you might think two expressions are equivalent, but there are cases where they have somewhat different behavior, or you can tell them apart. But with the left lambda, or immediate application of lambda, and let, for all intents and purposes, for anything we're doing, we're going to just consider those equivalent. So you could write either one. If you see let, you can rewrite it as left lambda. If you see left lambda, you can rewrite it as let. Shay is going to behave the same way either way. So it's up to you. It's a style thing. Okay. All right. So let's. Yeah, I think that's a good intro to one more thing I'd like to show you. Since we were talking about macros a little bit, let me show you another macro. Oh yeah, so here's a question: what does left mean in the context of left lambda? So that's me getting into Scheme jargon. I apologize for that. When I say left lambda, so when schemers are talking to each other, we have a shorthand for communicating very quickly what we mean by an expression. So if we say something verbally, the other person knows what we mean, so we don't need a whiteboard or something. So left lambda, that means a left parenthesis, and a lambda. So that's an immediate application or direct application of a lambda expression to an argument. So here's the lambda is lambda x times xx, and it's being applied to 7. Okay, so if you ever hear me say left lambda, that's all I mean. It's a direct application of a lambda to an expression, or to expression, which is basically an argument expression. I could write that as +3, 4. That's also going to evaluate the same thing. This, by the way, is different from just a lambda expression itself. This was another question that came up. So if you just have the lambda expression itself, Notice that the lambda expression evaluates to a procedure. It's not going to evaluate to a number like in the case above, because we're not giving the lambda expression an argument. And the other question that came up that's related is what happens when you expand lambda. We saw last time that the lambda expression just expands to a lambda expression. So there is a difference between having a lambda expression by itself. A lambda expression always evaluates to a procedure versus having an application of a lambda expression. And as Stephen pointed out, when we get into the interpreters, we will see more about this behavior. We will see sort of why there's a difference here. But sort of intuitively, what's going to happen is when we evaluate this procedure application, the lambda expression is going to evaluate to a plus 3,4 expression. That gets evaluated, and that's going to get evaluated to 7. The procedure is going to be a procedure that takes one argument and associates the value of that argument with 7. So we're going to pass in 7 as the argument. So what's going to happen is that x is going to be bound to 7 within the body of the procedure. So we have the body of the procedure times xx, and when we evaluate the body of the procedure, x is going to be bound to 7 in that case. So we're going to multiply x, which is 7, by x, which is 7. So that's what's going to give us the 49 back. So we have an additional mechanism that has to happen. So somehow we have to evaluate this sub-expression. We have to evaluate the lambda expression to get a procedure. We have to evaluate the sub-expression, which is the argument expression, to get back 7. And then we have to actually do the procedure application. We have to somehow associate or bind x, the formal parameter is what it's called, to 7, the value of the argument expression, and then perform whatever expression is, or evaluate the expression which is the body of the lambda, which is times xx. And each time we see a variable reference, a variable like x, we're going to have to look up the value of x to see if it has a value. If I typed y there, in this case, we would get an error because y doesn't have a value. But if I type x, we know that x would have a value because we're passing in 7 as the value of that x. So therefore, each time we see an x, we could, in our mental model, replace that with a 7. There are times where we have to be a little careful with that mental model, what's called the substitution model. If we get into mutation or mutating the variables values using side effects and things like that, then that breaks down a little bit. But we'll see all the details when we write the interpreters. Okay, so anyway, so lambda by itself is not, a lambda expression by itself is just going to evaluate to a procedure. It's not until we apply the procedure, call the procedure, that we're going to get back a value for it. So, and I can just, another way to show that is I can define, I can define f, that's the name of our function, let's say, to be the lambda x procedure. If I apply f to plus 3,4, now I get back 49. But f itself is just a procedure. So therefore, when we're trying to expand just the lambda expression by itself, we are going to get back a different expansion than the lambda expression applied to plus 3,4. Okay, so we should expect back a different expansion because they really do mean different things. Okay. All right. So let's take, since we're looking at macros and let and things like that, let me just show you, another macro or two associated with let, because we are going to have to do a little bit of macros when we get into the implementation of miniKanren. Not a whole lot. Basically, what I'm going to show you is probably sufficient, but we are going to need to see a little bit more than what we saw before with our let macro. So, if we go back, I defined this mylet macro. And you'll notice that, I had a pattern expression, or I had the pattern part of it, of the macro, and I had the expansion of it basically what we want to rewrite the macro to. This is called the template. Okay. And so what happens if I write my let x to be, let's see, 4, and I have the body is times xx. Max doesn't know how to indent my let. I haven't taught it yet. So what's going to happen at some level is that we're going to, or Scheme is going to evaluate the mylet expression, and it's going to say, hey, I see a left paren, so a left paren usually means a procedure application unless you have a macro or a special form. So a special form is something built in the scheme like lambda, okay, or let or something like that. Macros are a mechanism to let us define additional special forms, basically. A special form is just basically a type of syntax that has unusual evaluation rules. So the normal evaluation rules for Scheme is that if you see a left parenthesis, that usually means a procedure call. So we have a call to plus. Plus is a variable bound to a procedure. And now we're just going to evaluate that procedure call. We have to evaluate the sub-expressions. Plus evaluates the procedure. 3 evaluates the 3. 4 evaluates the 4. And then we call the procedure bound to plus with the arguments 3 and 4, and we get back 7. Okay, so plus. So this form is just the normal procedure application. That's the vanilla behavior you get when you have a left parenthesis. But there are some expressions, like a lambda expression. We know that behaves differently. This is not a procedure application. This is a special form, has special evaluation rules. We will handle this form especially when we write an interpreter, and we get back a procedure instead of actually doing an application. And same thing with something like let, which we know is equivalent to a lambda followed by an application, but we have special evaluation rules. So these, there's some special syntax here, basically. These parentheses do not mean additional procedure applications. This is not a procedure application. That's not a procedure application. This is a procedure application here, and this is a procedure application. So in this case with the let, the different parens mean different things. We have a procedure application, we have a procedure application here, but this procedure application is special because this procedure application in the body happens within the context of x being bound to the value of its right-hand side expression, or 7. So even though this is a procedure call, it's a procedure call in an environment where x is bound to 7. So even that behavior is special. So let is a special form, lambda is a special form, if is a special form, cond is a special form. We've already seen a number of special forms. Define is a special form. And you can see if something's a special form normally if you just type its name without parentheses. Say it's invalid syntax. So it's not saying it's not defined. It's saying it's invalid syntax. We're using it the wrong way. Okay? So macros let us define our own special forms. That's one of the purposes of macros, is so we can define our own special forms. And remember, there's a pattern and a template. And what happens is that when Scheme sees that we have a special form here following the parentheses, the name of a special form, now we're not doing the normal evaluation rules for Scheme, which we'll get into with the interpreter. But instead, we're going to treat this as a macro call. So what's going to happen is Scheme's going to look at, hey, we have a macro called mylet. So let's see if the expression matches any of the patterns. We can have more than one pattern if we want. So here we have a pattern. So we have mylet, and we have, some parens that actually match here, and we have the name of an identifier. I mean, if I want to make this a little more clear, maybe I should call this y. So we decided that we're going to have a variable in our pattern variable called x. That's going to match the y. So this is just like the pattern matching we did last time with pmatch. We have a variable e, and that's going to match this expression plus 3, 4. It matches that entire list. And then we have a body, and that body is this times yy expression. And now what happens is we rewrite, or we output a different expression, which is this left lambda, this direct application of lambda. So that mylet is Then through the macro call, I'm going to generate output. And it's going to turn it into a direct application of a lambda with the y. So this x is the same x that we had up there. So in this case, it's going to be the variable y. And that body is the body we saw before, which is times y. And e is going to be the expression e that we had before. I'm going to just grab it. And it's going to be exactly the same as if I had written, instead of this mylet expression, if I had written this expression down here. Now, that's a little bit of a lie. There's this mechanism of hygiene that we've probably talked about at some point that ensures that we don't actually have variable names that cause problems. So, if we have to introduce a new variable name, which this macro doesn't have to, we have to be a little careful with those names. So picking those names, we have to do it very carefully in a way to make sure we don't cause problems in our program. But scheme macros do that automatically. But basically, it's the same as if I had written this expression, and that expression evaluates the 49. Okay, so that's what the macros let us do. But you'll notice that our pattern is kind of restrictive here. In this case, the pattern only allows us to have a single variable binding. Okay, so that means that we can let bind one variable, but we're not allowed to let bind more than one variable. And in fact, we have to let bind exactly one. And in normal let, we don't have to do that. We can actually just bind no variables at all. So I can, for example, have no variable bindings and just add 3 and 4. That's a perfectly legitimate let expression. Or I can do things like say y is plus 3, 4, and z is 5, and w is times 3, 4, and then at the bottom I could have a list of y, w, z, or something like that. That's perfectly legitimate. I can have more than one binding. I could have 0 bindings, whatever. But our macro right now doesn't let us express this. Our macro expects exactly one binding. So if I change this let into mylet, called a mylet, now I get a syntax error because mylet doesn't know how to handle multiple bindings. So let's teach mylet how to handle more than one binding. And there's this amazing syntactic extension in the pattern matcher that allows us to do this very easily. All we do is add dots after this pattern. So the dot, dot, dot has to be 3 of them. The dot, dot, dot means that whatever comes before it can appear 0 or more times. It's 0 or more times. So we can have 0 or more binding here. And now, where we split up the x and the e, we have to put dot, dot, dots in the template as well. So I had an x, and that was part of the dot, dot, dotted expression. So now I can have 0 more of these x's. And similarly with the e, I can have 0 more of those expressions e. Now let me try my mylet, and it actually works. Okay. So that's a very powerful extension to the pattern matching. So this matches 0 more of the things that come before. We just have to make sure that in the template, we match up anything in the pattern that has the dot, dot, dots. They need to get their dot, dot, dots as well. Otherwise, the macro is going to complain. So if I forgot my dot, dot, dots for the x, it's going to give me scheme will give me an error saying missing ellipses. That's what the dot, dot, dots are called in the syntax form. So I have to make sure that I have some dot, dot, dots there. But the nice thing is now I can handle any number of let bindings. So I can do this as well, any number of variable bindings, and that works just as well. Okay, so so let's just remember what that means. So it means that this let expression is equivalent to writing left lambda, immediate application of lambda. This would be x, z, w, as our arguments. And the body is going to be the call list YWC. And we're passing in as arguments +3, 4, and 5, and ×3, 4. Okay, so the 3 arguments are argument expressions to this call, to this lambda. And that gives us the same value. Okay, so you can start to see that macros are very nice in that they allow you to extend the syntax of Scheme in a very powerful way. And you can have the shorthand notation. This is quite nice to be able to do this sort of pattern matching. I'll show you one other type of macro, and I think that's probably all the macroness that we're actually going to need for the most part. We might look a little bit at hygiene another time. But I'll show you one other thing that you need to know about in order for us to do the scheme macros for miniKanren a little bit later. And it's also just nice to see that you can do this in Scheme anyway. So we're going to write a recursive macro. So the macro that we wrote before, it had the ... dots in it, so we can have any number of bindings, but the macro wasn't written in a recursive fashion. We're not calling mylet inside the template. Okay, but we'll write a somewhat more complicated macro. It gives a little more of the feeling of what macros can do. And so what I'm going to show you is another form, another spell. And we can see it's a special form. If I type let star, I get invalid syntax. Okay. If I just typed let foo, I get a different error. It says variable let foo is not bound. So let star is defined. Scheme knows what it is, but it's not a procedure. It's not like plus. Plus is a procedure. But let star is a special form. It has special evaluation rules. You don't treat it like a procedure call when you see a list beginning with it. So let's look at what let star does. Well, in order to understand what let star does, we have to understand a little more about the behavior of let. So I can say let x be +3, 4, and I can say let y be 7, let's say, and then I can say the body is list xy. Fine. However, what I can't do, or it won't work the way I think it does, is I can't write let y be the value of x. That might seem to be a natural thing to do. So all right, whatever x is, I want y to have that value of x. If I try running that, evaluating that expression, I get the error that x is not bound. So what's going on here? Well, let's remember what that let turns into. So that's the same as doing let a left lambda xy with the body list xy. And we're applying that to these two argument expressions, +3, 4, and the binding of y, which is x. Okay, that's equivalent to this expression. They should have the same exact behavior, the same exact value. And sure enough, I get the same behavior. I'm not, even when they don't have values, I get the same behavior. I get the same error message that x is not bound. So these expressions are equivalent in that way. I get the same error messages when I do something wrong. So what's wrong? Well, if you look at this x does not occur within the body of that lambda. Okay, so within the body of the lambda expression, x has a meaning or has some value associated with it, whatever was passed in as part of the procedure call. Y has a value. Y has whatever the value passed in. But here, x has no value at all. We haven't defined x at the top level. There's no notion of what x is. So Scheme doesn't know what x is bound to, so it's going to complain. So the rule for evaluation for let is that the right-hand side expressions are now allowed to refer to the value of the variables on the left. Okay, so I'm not allowed to do that. That doesn't make sense. Now, what I could do is have another let on the outside. I could say let x be 5 on the outside, and then have a let inside. And now this is perfectly legitimate because that x is now going to refer to the x up here. So that x will be 5. So this has a value now. But the point is, this x is not going to refer to the value of the x that's bound in the same let expression. And another consequence of this is, whoops, another consequence of this is that I can actually reorder these let bindings, and it doesn't shouldn't matter. Okay, so I swap the binding of x and y has the same value. It doesn't matter because that's the same as swapping the order of the arguments in the lambda expression. If I go back to my lambda expression, let's say I pass that as 5 or something, that's fine. I can swap the order of x and y as long as I swap the order of the arguments being passed in, and I have the same value. So that the order of the arguments to lambda doesn't matter as long as I'm careful to also update the order of the arguments passed in to lambda. Okay, so with let, the bottom line is I can't refer to the binding of another variable that's being let bind. It's bound at the same time within one of the bindings. So this binding for y can't refer to the binding of x. All of these get evaluated at the same time, if you want to think of it that way, or in parallel, or whatever. So actually, the semantics of scheme are a little trickier in that you don't actually evaluate them in parallel. But if you didn't have any side effects, in theory, you could do that and not get caught. But anyway, this is really our first introduction to the notion of scope. So this variable x is bound to this x. This x here is bound to the value of this x up there. So, so we actually have two different x's here. So we have the x in the body of the innermost let, and then we have the x bound in the outermost let. So this x is equal to 5, and then this x is equal to 7. They're actually, even though they're both called x, they get different values. So we're allowed to what's called shadow the variable x. So we might want to have a form of let that allows us to play this sort of game where we're allowed to, it's a shorthand for nested lets, basically. And as long as we have that sort of shorthand, then we can play these sorts of games. So maybe what we really want to do is, instead of writing this let expression, which is basically illegal because this x doesn't have a binding, instead, maybe what we really intend to do is have nested lets. So we could have another let expression. Now we have nested let expressions. Okay, so now this should be okay, except I get the parentheses wrong. Oh, okay. Okay, so this is fine to have these nested lets, because now I can refer to this x, and that's getting the x from the previous, the outside let expression. Okay, so this let expression evaluates x is going to get the value of 7. Now y will get the value of x. Well, we looked that up. X is 7. That's fine. And now we say a list containing x. We can look that up. That's 7 from this binding. And y is going to be the value of x, which is also 7. So we get 7, 7 in this case. So we might want to have a special version of let, which basically turns into these nested lets. Okay. And in this case, the ordering of the bindings does matter. And this is called let star. So this is already built into scheme. So I could write let star x to be +34, y to be x, and list xy. And I get back 7, 7. And so this let expression is exactly equivalent to this let up there. And so let's try expanding it. Let's see if that's true. And that's a little hard to read, so let me turn off the gensims. Okay, and sure enough, you can see that the expanded code has two let expressions and then they call the list. So this let star expands into nested lets, and we can have as many let bindings as we want. So now we could have we could have another x which happens to have the value of y, and we can keep playing these games, and now we'll have 3 expansions of let. So what we want to define is a macro for let star that will turn into these nested let expressions. Let's see if we can figure out how to do that. So when we define a macro, well, I'll call it my let star. Remember, we have to use define syntax. I messed it up before. Instead of define. And we have to write one or more pattern template pairs. Okay. So when we're thinking about this is going to be a recursive macro because we don't know how many bindings we're going to have, and each binding is going to have to turn into its own occurrence of let. So what we want to think about is what our base case might be. What might our base case be? Well, let's think about that a second. Well, what's the smallest number of bindings we can have? 0. The let star with 0 bindings, and that's the same as let with 0 bindings, basically. Basically, we just evaluate the body. And we can see what let star with 0 bindings evaluates to. Let's try expanding that. Okay, so it just expands to the body. This is the built-in definition of plus. All right, so when we're defining our macro, we can have one pattern, which is going to say, all right, we have no bindings at all. So empty list of bindings, but we have a body. And we can just expand to the body. In fact, that itself is a complete macro. So like I had this let star, I can define a my let star, and it should work now. Sure enough, that works. But that only handles the case when we have no bindings. That's our base case. That's when we've handled everything else. In order to handle one or more variable bindings, we're going to have another case. We can have more than one case with syntax rules, just like we can have more than one case with our pattern matcher, with pmatch, or when writing with regular recursive definition, pond or something like that. So in this case, we're going to have some variable x bound to e, and we also might have more than one binding. We could have additional ones. And so now I'm going to use notation again. So basically what this says is that we have at least one binding between a variable x and some expression e, and then we have 0 more additional bindings. And I'm just using this x star as a convention, saying that, this could be any number of those things, give any number of additional expressions. And we have a body. Okay, so we're using our friend ... And now I'm going to figure out what this expands to. Well, we know that let star is going to expand into nested lets. So we're going to have a let with a binding between x and e. And we have to handle all the rest of the bindings. Well, so to do that, we can make a recursive call to mylet. And the bindings we have are going to be and we still have the same body. All right, so let's see if we got that right. Here's our let star, and let's try my let star. Yep, sure enough, we can now handle multiple bindings. We can now handle no bindings. And so we've added a syntactic extension to our language. We have this new form, my let star. That's a recursively defined macro. And we use the ... that we saw before for handling multiple bindings in let. Now this allows us to tear apart when we have one or more bindings in our recursive macro. Okay, so the syntax here is a little strange if you're not used to it, but if you write a few of these macros, you start getting the hang of it. And the recursion actually is pretty simple in this particular definition. You can write all sorts of really hairy macros, but the ability to use recursion in our macros is very powerful, just like it's powerful when writing functions or procedures. So when we get to miniKanren, we're going to see that we have some recursive macros, and after seeing a few more of those, hopefully that will help make sense of this. All right. So in this talking about let and let star and left lambda, immediate application of lambda, we got into this idea of variable scope and whether or not a variable is bound or not. And so let's just look at some simple examples. So here's a lambda expression. And let's say I've got lambda xx. That's the identity function. Okay. So if we remember, we got some different parts of this lambda expression. So we have this list up top of the variables, or identifiers. And so this list is a list of the formal parameters or the formal identifiers, if you want to get it sort of in the technical terms. Okay. And then we have the body of the lambda expression. And in this case, we'd say that x occurs bound. So this is an occurrence of the variable x, and occurs within the scoping, or within the scoping of this identifier, basically. So the way it works for the lambda expression is if a variable appears in the formal parameters, then it's considered bound within the body of the lambda expression. So in other words, when we do a procedure application, if x happened to be bound to 7, then this occurrence of x inside the body would be bound to 7. Okay, no problem. If I were to replace the x with y, then we would say, in that case, y occurs free. So in this case, y is not bound by x. Y is not in the formal parameters list. So x occurs free. It doesn't have a value. There's no value associated with it. If we did a procedure call and we passed in, 5 as the value of x, then y would not be bound in this case, and you would actually get an error. You get an error with y being unbound. So let's just try that. Apply that lambda expression to 3. So now x is going to be bound to 5, but we get an error saying that variable y is not bound because y occurs free. If I replace the y with x, then we get back 5. Of course, I can have multiple variables bound. And I can pass in multiple values here. So now x is going to be bound to the value of this expression plus 2, 3 when I do the procedure application. So x is going to have the value 5. Y is going to be bound to the value of 6, which is just 6. And so when I add x and y, I'm going to be adding 5 and 6, and I get back 11. So that works. Okay. And another important thing to realize is that I can have nested lambda expressions. So I could have lambda x, and then the body of the lambda x could be itself a lambda expression, lambda y. Now if I add x to y, x occurs bound within the context of the outer lambda expression because x appears within that list. Y occurs bound within the context of this inner lambda expression. We have y, okay, because we have y there. If I pulled out the lambda and sort of ignored where it came from, in this context, this occurrence of x is occurring free, and this occurrence of y is occurring bound because of the lambda y. But if I wrap the lambda x around it, then both x and y, those occurrences are both bound. Okay, so this idea of free and bound is very important. And basically, if you want to see if a variable is bound, you look at your program and you start looking inside out from the use of the lambda of the variable, and you see, is there a binding form? Is there a lambda? Is there a let? Is there a let star? Is there a let rec? To see if there's some definition. Let rec allows you to define recursive functions. Okay, so in this case, I can see, no, x is not bound by that lambda, but it's bound by this lambda up top. So yes, x occurs. This is a bound occurrence of x. That's fine. I can also do things like have shadowing. So I could call both of these x. Now, if I want to see where x is bound, I go inside out, and I find immediately that I have this binding for x. So this occurrence of x is bound to that x right here. And now this occurrence of y is not bound at all. We don't have any sort of binding for y. But of course, I can add in one. I could say lambda y. And so it's important when you're looking at your code and trying to figure out if variables are free or bound, that you're working inside out. So the y is bound to this y up here, this binding, and the x is associated with this innermost binding. And this outermost x actually is being ignored. So we call this shadowing. So this x, this innermost x, shadows the outermost x. And so whatever value of the innermost x, that's the value we're going to look up in our addition expression. All right, so that gives us back a procedure, that whole expression. So let's try feeding in some arguments. I'm going to apply the outermost procedure to 1, value 1. That gives us back another procedure. So another procedure call. So that outermost x can have the value 1. I'm going to make another procedure call with the value 2. So now y is going to be bound to 2. I get back another procedure because we have 3 nested procedures. Now I'm going to apply 3. So this innermost x is going to have the value 3. And therefore, when I'm adding x and y, I'm going to add this x, which is bound to 3, the value of this y, which is bound to 2, and therefore I get back 5. Okay, so we're ignoring the value of the outermost x in this expression. That doesn't matter. It's getting shadowed by the innermost binding of x. And of course, I could write this. Maybe it's a little easier to read if I write this as nested lexical. This is equivalent to what I wrote before. And then the body is plus xy. Back 5. This x bound to the innermost x binding of x. This y is bound to this y. And the x up here, x being bound to 1, that's irrelevant. Doesn't matter I called it x. I could have called it foo, and I would have gotten the same answer back. It didn't matter. And of course, since we have nested lets, I could rewrite this using our friend let star. I'll show you how I would have written that. And this also has the same behavior. And so with let star, you evaluate these top down, the bindings top down. So x is 1. Now y is 2 in an environment where x is 1. And now here, x is 3, and y is 2, but we're shadowing the x being 1. Okay, so all 3 of those are equivalent. I could use it with left lambdas, a direct application of lambdas, nested lambdas. I could write it as these explicitly nested lets, or I could write it with let star. All those expressions are equivalent. They have the same meaning. They'll give me the same errors if I leave things out. And I could have also, of course, used my fancy let star. And this should work just as well. And sure enough, it does. All right, so that's the notion of a variable occurring free or variable occurring bound. And we've seen the notion of shadowing. And the type of scoping, this has to do with, what we're talking about, something called variable scope. Variable, the scope of a binding, whether or not variables are occurring free or occurring bound, occurring free or occurring bound. It's the whole notion of variable scope. And Scheme has what's called lexical scope or static scope. So we can just look at the code and immediately tell the binding structure of the code just by looking outside for binding forms. And I should remind you that let is a binding form, let star is a binding form, lambda is a binding form. These are all binding forms. There's another one, let rec, that's a binding form. So I could have some combination of these. So I could say lambda x, and inside of that I could have a let y be x, and I could have a let star here of w to y, and maybe another binding of b to w. And now I could have like a list of x, y, w, v. And I could apply that whole thing to 5. So now we have different binding forms, but the idea is still the same. And we can see we get back all 5s here. So what's going on? So we're creating this list, and what's the value of x? Well, x isn't bound in the let star, so let star has bindings for w and v. X isn't bound in this let because that's the binding for y, but there is a binding for x in this lambda. So when we do this application, procedure application, x is going to be bound to 5. Okay, what about this w? Or sorry, this y? Where's the y bound? It's not bound in the let star. Those are bindings for w and v, but it is bound here within this outermost let. And the value it's going to get is the value of x. Well, where does this x come from? X comes from the lambda binding. Okay, so x is going to have the value of 5. Y is also going to be 5. And in fact, as we trace this down, we'll see that they're all bound to 5. That's why we got that answer. Okay, so but we can play the same game for all of these. But we do have to remember that there are somewhat different rules for the different types of binding. So like a let versus a let star, they actually have different rules. If I wanted to say let, let's see, I could call this z. If I say let z be y, that would work just fine in a let star. But in a let, because these are not nested lets, a let star is equivalent to nested lets. In this case, that y is not bound to y. So let has a different binding structure than let star. So this y actually is a free occurrence of y. And if I try running the expression, evaluating it, I'll see that variable y is not bound. So, it's important that you understand what the binding structure is for each of these different forms, for lambda, for let star, for example. And you should be able to look at the variables and try to figure out, is this a free occurrence of the variable? Is it a bound occurrence of the variable? If it's a bound occurrence of the variable, where is the binding? So this occurrence of y is a bound occurrence of y, and the binding is to that y. Okay, so just work inside out. And so this is an important skill, and as we write the interpreter and deal with issues of variable lookup, this will become critical. And in particular, we're going to be dealing with the notion of environment binding. And basically, we're going to have a notion of what's called an environment. So if I go back to the previous version of this that actually runs, we're going to have an environment that we keep track of. And we can start, representing this environment basically as a list of values, like a list of cons pairs, that kind of thing. So we'd say, maybe initially we have no bindings for any of the variables. But here we have a binding between x and 5 once this application has happened. Once we apply this 5 to lambda, then within the body of the lambda expression, x is going to be bound to 5. So this is one representation we might use for an environment. Anytime we would look up x, we would look x up in the environment and we'd find that it's bound to 5. Okay, so this is a concrete representation of this idea of an environment, but the idea of an environment is that we have an association between variables and their values within a certain scope. So at this point, we're going to let bind y to have the value of x. So now we can extend the environment even more. So there's an association between y and 5 and x and 5. Both of those variables have the same value. And we can keep building up the environment inside the scope. Now that environment's a little boring, so I'll just show you one more. We might say x is plus 2, 3 within this let expression. And I'll do some nested lets here. Y is times xx. And z is x plus y. And then we're going to have the body is the list of x, y, z. Okay. So let's see what's going to happen for this environment. So we could say we're going to start out with the environment being empty. This is the empty environment. When we start out, there's no bindings for any of these variables. Technically, there are some bindings because, for example, plus is actually bound to the addition procedure, but we're going to not worry about that. We're just worried about the variables we're introducing. So we'll say initially we have the empty environment. We're outside any of these bindings. Now we're going to be associating x with the value of this expression, which is 5. And the scope of that binding of x to 5 is the body of the let expression. So within the body of this let expression, we have an extended environment where x is going to be associated with 5. Now we're going to evaluate y being times plus times xx, x times x. So in order to evaluate this expression, we have to look up x in the environment. And we find out that x is bound to 5. Okay, so since x is bound, we can do this variable reference and this variable reference and get 5 each time and multiply 5 by 5. So y is going to be bound to 25. Whoops. So now we'll see that y is bound to 25. 5. This is our extended environment. We're building up as we go. And now we've got z or z, depending where you come from. So the value of z is going to be x plus y. So we look up x in the environment. X is bound to 5. We look up y in the environment. Y is bound to 25. So we can actually do the addition. We're not going to get an error looking up those variables. So now z is going to be bound to 30. So now we extend our environment some more. So we have the old environment, and we're just adding an extension. So now z is 30. So now we're going to do list of x, y, and z. So x is bound to this outermost x, which has the value of 5. Y is bound to this y right here, which has the value of 25. And z is bound to this z right here, which has the value of 30. So we can look at each of those up in the environment. So x is 5 right here. Y is 25, which is right here. Z is 30. So we should get the list 5, 25, 30, and indeed we do. We should probably make one more point. Let me add one more let binding, and I'll say x is going to have the value of z. And now we'll have the same body, x, y, z. So what happens now? Well, with this innermost binding, we're going to bind x to the value of z. If we look up z in the environment, we get z is 30. Okay, so now x is 30. So now we extend the environment with a new binding between x and 30. Now, if you'll notice, x appears in the environment twice. We have the association between x and 30, and we had our initial association between x and 5 from all the way up here. So we've shadowed the old value of x. So x being 5 is no longer visible within the body of this let expression, the innermost let expression. So when we create the list, this x is going to be bound to 30. We'll look at the list from left to right, and if there's a duplicate, well, we'll never reach that duplicate expression. We'll always see the duplicate variable binding. We'll always see the binding on the left. So therefore, we'll get back 30, 25, 30 this time. And sure enough, that's what we get. So to make it clear what's going on, though, it's not like we have destroyed the old version of x, the binding of x to 5. That value is still around. So I will show you an example with the shadowing. So I could say let x be plus 2, 3. And then I'll have another let x to be, I don't know, 7 or something like that. In this case, if I just return x, I'll get the innermost binding of x, 7, because we shadowed the outer one. But what I could do is the following. I could create a list containing the value of this let expression and containing the value of the outermost x. So this expression might look a little complicated. Let's break it down, what's going on. So we have a let expression where we know that x is going to be bound to 5. So let's look at our environment. X is bound to 5 within the body of this let expression. Okay, and this called a list is within the body of the let expression. So x is bound to 5. Great. We're calling lists. We're building up a list, link 2, hopefully, these two sub-expressions. With the first sub-expression, we have to evaluate that according to our normal rules. And here, x is going to be bound to 7. So inside the body of this innermost let expression, we have an environment where x is bound to 7, and we have the old association of x to 5, but we can no longer see this x. It's been shadowed. So when we look at